So welcome everybody to tonight's prestigious lecture. Just wanted to say that even though the tube drivers appear to have gone underground on us today, you haven't. So I'm really glad that you actually managed to make the effort to get here. It's much, much appreciated. And I do hope you enjoyed the lectures this evening. Just a few words of introduction. I'm really delighted to welcome Professor Emily Shukra here today, this evening. She will be presenting on the theme of climate change with the title, The State of the Climate and Humanity's Response. So I'm really looking forward to hearing Emily today. Just a few words of introduction about Emily. She is the director of the Cambridge Zero, which is the University of Cambridge's major climate change initiative. She also is a professor of the environmental data science at the Department of Computer Science and Technology at Cambridge. So her background, she is a mathematician and a climate scientist, a fellow of Darwin College, and I gather there's a few other Darwin Collegeites here today as well, so welcome to them as well. So a fellow of Darwin College, a fellow of the Cambridge Institute of Sustainability Leadership, an associate fellow of the Centre of Science and Policy, a fellow of the British Antarctic Survey, and a fellow of the Royal Meteorological Society. So at the University of Cambridge, she is director of their UKRI Centre for Doctoral Training on the application of artificial intelligence to the study of environmental risks. She's also the academic director of the Institute of Computing for Climate Science, and co-director of the Centre for Landscape Regeneration. So I don't know how you managed to fit this all in, actually. It's quite impressive. She has worked in the past, for over a decade in fact, for the British Antarctic Survey, where her work included leading a UK national research project on the Southern Ocean and its role in climate. Prior to this, she took up a research position in Paris and also at MIT. So she also acted as an advisor on climate to the UK government in various capacities. And finally, she was awarded for services to science and the public communication of science and OBE in 2016. And finally, I'm very glad to say that she is a co-author of a book as well. So, co-authored with none less than His Royal Highness King Charles, together with Tony Juniper, and that's the Lady Bird book on climate change. So, I'm sure you will all rush out and buy it tomorrow. Long may you enjoy it. Thank you, everybody. Look forward to hearing you speak. We will then listen to Peter Flynn. Peter Flynn was the president of the institution the year before myself, the 136th president of the institution, and I'm sure is known to many of you here in the room today. Peter will present a report that we've just published, and I think a copy is available. We have some copies that you can take away if you wish to, but it's also available for those of you who are listening online, rather, you can actually download a copy, I think, from our webpage. So I do encourage you to do that if you so wish. So, back to Peter. Peter has a broad career in a large number of engineering areas. So aerospace, automotive, rail and process, and he's provided leadership in all points of the technology life cycle. So right through from research to product development, manufacture, all the way through to field support, so the full gambit. Most of this has been in private industry over his career, but he's spent the last 10 years working between business, university and government and looking at the relationship between those different branches. And that has given him a very wide perspective of engineering with innovation and business as the common threads. I would encourage you to seek out his book, which is entitled Managing Technology and Product Development Programs, which was published in 2019. I'm sure it's regarded as the Bible in that particular field, Peter. So educationally, if we look back a bit further, he read mechanical sciences at the University of Cambridge and then took an MBA at Strathclyde Business School. He also attended the Senior International Management Programme at the Harvard Business School. So his career has been in a number of areas, as I've mentioned. He's worked in total for 4 companies and operated as their chief engineer, director, and managing director level, with companies latterly having a turnover up to 100 million. So quite an impressive CV there.
From 2007 to 17, he worked at the interface between industry, government, and universities, and provided leadership to a number of quite high-profile projects. The setting up, for example, of the Manufacturing Technology Centre in Anstey, a similar role for the High Value Manufacturing Catapult project, and as interim director for the Aerospace Technology Institute, a body charged with overseeing the UK aerospace R&D programme. And finally, he was also chairman of the advisory board for the Intelligent Automation Centre at Loughborough and Cranfield Universities over a 5-year period. So, Emily, it gives me great pleasure to invite you up to the lectern, and I most look forward to listening to your lecture now. Thank you.
Well, thank you very much, and it's a pleasure to speak to you this evening, both in the room and those people who are listening online. Really, this is very much a double act that we're doing this evening. So I'm going to, if you like, give you the big picture and what I hope is some inspiration for the role in particular that mechanical engineers could be playing in terms of the net zero response. And then Peter's going to follow on from me and give some more details about some of the things that engineers are already involved in and future prospects as well. So let me start off with the state of the climate, and I wanted to, we're actually right at the moment, many of you will be aware, there's a very large climate conference going on in Egypt at the moment, COP27. It's COP27 because it's the 27th of the conference of the parties of the signatories to the United Nations Framework Convention on climate change. And that really came about 27 years ago, or thereabouts, in part in response to the very first report of the Intergovernmental Panel on Climate Change, which came out in 1990. So this is 30 years ago. And I put up here one of the key statements from the executive summary of that report that very clearly said, even in 1990, that emissions resulting from human activities are substantially increasing in the atmospheric concentration of greenhouse gases, and it was very clear that this would result in an additional warming of the Earth's surface. Unfortunately, in terms of the geopolitical response to that very clear statement, even back then, in terms of the science, the geopolitical response has been rather slow over the last 30 years. So roll forwards to today, and we're starting to see the impacts of climate change very clearly in terms of extreme weather events around the world. And we're now in the have just completed the 6th cycle of the IPCC reports. And last summer, Working Group 1, which is focused on the physical science aspects of climate, report came out, and I've just put a quote from that report that human-induced climate change is already affecting many weather and climate extremes in every region across the globe. And just look at the last few months, we saw extreme heat wave in the UK, temperatures exceeding 40 degrees Celsius in a number of locations across England, records also in Scotland and Wales. We've seen record rainfall in parts of the world, including severe flooding in China and really deadly flooding that's continuing to affect communities in Pakistan. So some of the impacts of extreme weather that we've just seen in recent months. This is then, if you like, a dashboard of how the world has changed over the last 170 years now, going back to 1850. What I've shown here is just 4 key indicators of, if you like, global society, but then also how our climate has been changing in response to that. And I particularly highlighted that 1990, you can see it in the red line, just to see how much change there's been over the last 30 years since that first IPCC report came out. So in blue you see, I guess, an indicator of human society. We've seen this massive increase in global energy use over the last 150 years, and a really substantial increase just since over the last 30 years, since 1992. Now, of course, to date, the vast majority of that energy use has been as a consequence of the use of fossil fuels. And so, consequently, we've seen this really dramatic increase in the amount of carbon dioxide in the atmosphere. And again, if you look, you can see a very substantial increase just in the last 30 years. Obviously, it's greenhouse gas, and we've consequently again seen a dramatic increase in temperature. And once again, I want to just highlight that really significant change in the last 30 years. And it's not just temperature. We've also seen a dramatic increase in sea levels as well, and that sea level rise coming about over much of that time period as a consequence of a combination of the ocean water in the oceans warming up and thermal expansion leading to sea level rise. But increasingly over recent years, that sea level rise has been as a consequence of melting ice, particularly melting ice in the polar regions, and that's forming an ever larger percentage of the sea level rise that we see each year. So the loss of ice from Greenland and Antarctica in particular is accelerating, which is, of course, a really dramatic concern. And you can see here some satellite imagery showing where that greatest loss of ice from both Greenland and Antarctica is. The areas of both places where you see red regions are the regions of greatest loss of ice. If I focus in particular on the Antarctic, if you look at the area of significant red in Antarctica on the bottom left-hand side of this map, Antarctica is cold, and actually the greatest cause of that loss of ice is not melting of Antarctica from above. It's where warmer ocean water around Antarctica is getting underneath the ice sheet and melting it from below. And some of the greatest uncertainty in terms of our understanding of what the future of that ice sheet might be is understanding exactly the mechanisms associated with that melting, how it might progress into the future, and the structure of the ice sheet itself. So one of the greatest uncertainties is associated with the front of the ice shelf, and where that starts to collapse into the ocean as you get the melt. And there are possibilities of that being a really significant instability that could potentially significantly speed up the loss of ice. And the concern is really that both Greenland and that West Antarctic ice sheet hold within them currently the equivalent of many meters of sea level rise. And we simply at the moment don't have a good understanding of exactly the timescale at which that sea level rise might be realised. But it's one of the greatest causes of concern. The Arctic has seen really dramatic changes as well. And partly the reason that the Arctic and the Antarctic are so much more changing than the rest of the planet, they're changing at a faster rate than the rest of the planet, is in part through a variety of different processes that are broadly called polar amplification. The most intuitive, I think, of which is simply that ordinarily ice is a very, very reflective surface, but when it melts, it turns from a very reflective surface to quite an absorbing surface because you have a much darker ocean left behind, and that is in part one of the key processes that acts to amplify the warming in the polar regions. And we've seen this really dramatic loss of sea ice in the Arctic over recent decades. The graph up there is the satellite record since 1979 of the sea ice extent in the Arctic at the end of the summer melt season each year in September. And the other cause, which is also a cause of really significant concern of increasing carbon dioxide levels in the atmosphere, is ocean acidification. And we've seen a really dramatic increase in ocean acidification that's exactly mapping the carbon dioxide increase in the atmosphere. So in this graph here, you can see the red graph is the atmospheric concentration of carbon dioxide, and the blue is the pH of the ocean measured at a particular location, just off Hawaii actually. So that's the current state of the world that we're seeing across many, many different measures, really dramatic changes in terms of the current state of the climate. What are the projections into the future? And again, I've got a quote here from the most recent IPCC report. Global warming reaching 1.5 degrees in the near term would cause unavoidable increases in multiple climate hazards and present multiple risks to ecosystems and to humans. We're currently between about 1.1 and 1.2 degrees of warming, and actually there's an annual report by the Global Carbon Project, which will be released tomorrow morning, which looks at the amount of carbon budget we have left before we would be likely to exceed 1.5 degrees, and that report is going to be saying that effectively we've got about a decade left in terms of our current rates of emissions, in terms of the period of time in which we're likely to exceed 1.5 degrees. I've already mentioned some of the causes of exceptional concern in terms of the polar regions. We know that when the world has been not much warmer than it is today, that those ice sheets that cover Greenland and Antarctica have not been fully intact, and that sea levels have been many meters higher than they are today. But there are other significant causes of concern that are often characterised as being tipping points, but effectively parts of the climate system that can either, we know, be in two different stable states, and so there's a potential to flip from one stable state to another, or parts of the climate system that are effectively irreversibly changed. Ice sheets are one of them. The Amazon rainforest is another. There's a concern that it might switch between being a carbon sink and a carbon source. In fact, there's some indication that that might already be happening. So switch essentially from a rainforest into a more savanna type ecosystem, which in itself would have a really significant effect of accelerating climate change. And the bottom image that you see on the right-hand side over there is a lake in the Arctic, and that circle, the white circle that you can see, is a bubble of methane coming out of that lake in the Arctic. In the Arctic, there are vast stores of frozen methane in lakes, at the bottom of the ocean, and also in the permafrost. And the concern is that as the world warms up, then those frozen stores of methane may be released into the atmosphere. There's actually concerns not just about the Arctic, but also tropical wetlands, for example, releasing more methane as they warm up. And methane is much more powerful, albeit shorter-lived, greenhouse gas than carbon dioxide, and similarly could act as a significant acceleration of climate change. And in fact, in terms of the current measurements of methane, we've in recent years seen a very significant uptick in global atmospheric concentrations of methane for reasons that are not fully understood, but there's certainly some concern that some of these feedback processes may already be taking place. Okay, so that's the kind of global state. How is that then translating into things that affect us here in the UK? If we look at this last summer, where we saw significant periods of extreme heat, that extreme heat we know can particularly affect elderly people, and the early conservative estimates from the Office of National Statistics is that over those periods of extreme heat, there were coming close to 3,000 heat-related deaths, particularly amongst the elderly in England. We've also, in recent years, seen repeated episodes of severe flooding across the UK, and that's led to real devastation and destruction, but a particularly significant financial costs. And so, on average, it's now costing about £1 billion per year in terms of the cost of severe flooding events. There was a particularly bad flooding events in the winter of 2015-16, where the costs were even higher. We're also seeing the impacts in terms of the impacts on various different aspects of our wildlife in the UK, and in particular aspects of our wildlife that we depend on for their services, not least critical pollinators, as well as the impacts on our agricultural system. So periods of extreme weather, whether that's heat waves or droughts or flooding events, each have a significant impact on our agricultural productivity. And then the final two examples that I have here are also really important and only just starting to be fully understood, and that's essentially the knock-on impacts in different ways. So the first aspect is where we're starting to understand cascading risks, in particular looking at how critical infrastructure can be impacted by cascading risks associated with climate change. The example here is actually a photograph from a flooding event that happened about 7 or 8 years ago now, and that's an electricity substation just outside Gloucester that came very close to being taken offline. Not only does it provide power to 500,000 local homes and businesses, but it also, for example, provided power to the local sewage treatment works. So it wouldn't have just been without electricity, it would also have been without sewage treatment, and etc. So you can very easily get these knock-on cascading impacts, which we're only just starting to really properly understand. And then, of course, the other area is the way in which the UK can be impacted by climate change that is happening elsewhere in the world. And that could be about migration as a consequence of climate change. It could be that climate change can be one of the key drivers of local conflict, and it can also be that climate change ends up affecting global food prices, which then affects us in the UK. I thought I'd just say a little bit about climate science and the ways in which climate science has been used to build our understanding both of climate change today and how the climate might evolve into the future. This is me in the Southern Ocean. As I said, I spent a long time studying the Southern Ocean and in particular how that's changing as a consequence of climate change, but also how it has a global impact. So there's essentially one set of research on the climate science side, which is very focused on measurements, and then there's another set of work that's very much focused around numerical modelling. And I've included here work that I'm involved very much with on the numerical modelling side of things now, which is very much around how we supplement the traditional physics-based numerical models of the climate system with data-driven models, and in particular the cutting edge of much of climate modelling now is how, as so many fields, how we can use artificial intelligence, machine learning to improve our climate-related models, incorporating more of the observational measurement data. I've just got one example on each of those, on the measurements and on the modelling of some of the really most important measurements and most important modelling that's being undertaken associated with each. This is, in many ways, I think, one of the most important measurements that's taken, and this is from ice cores drilled in Antarctica. And the photograph that you can see, those little white dots there, this is a slice through an ice core, and the little white dots are bubbles of air. So what happens is that in Antarctica, the snow falls in Antarctica, and as you drill down through the ice, it means that you're able to look down through the layers of snow going back in time and recover the actual air that was in the atmosphere hundreds of thousands of years ago. And those bubbles are ancient air. And then we analyse the composition of that air. And the graph that you see here goes back 800,000 years and shows the levels of carbon dioxide in the atmosphere over the last 800,000 years. And you can see from this, you can see a natural oscillation, but you can also see where today's levels of carbon dioxide are. We know that today's levels of carbon dioxide are the highest in at least 2 million years, probably a lot longer, from data such as this. It's one of the clearest pieces of evidence we've had to show just how unusual current climate change is. So that's on the measurement side of things. On the numerical modelling side of things, the critical thing about numerical models is that they are absolutely central to our ability to be able to predict the future and to understand what different future emissions pathways might mean in terms of the impacts of climate change. And so they're a key input into policy-related decisions, both in terms of the level of ambition of emissions reductions that are required globally, but also critically in terms of understanding at a regional level what sorts of adaptations and resilience building measures need to be put in place to respond to the extreme weather events that we're already starting to see and we're likely to see more of into the future. It's actually different information that you need for both those questions. So in terms of the level of ambition of global emissions reductions, the key indicator that's used in policy is global average surface temperature. But if you come to understanding how to build resilience to climatic changes, then actually global average surface temperature is not a very useful quantity because it doesn't tell you about the climate impacts of a particular location. And so for informing adaptation and resilience building, you need to go beyond that global average picture to understand the impacts of extreme events at a particular location. And so actually that's one of the reasons that we're starting to more and more use AI and machine learning to incorporate more data to improve our climate model projections at a local level in terms of those extreme weather events. And this is just some of the most recent climate modelling outputs. The very top graph on the left-hand side here shows the projections under different future emissions of greenhouse gas scenarios. And then you can see how that maps into different regional changes in temperature. And then the bottom figure here is one that's perhaps more pertinent to building resilience, and it then looks particularly at the risk of extreme events in particular different locations. So different information from the modelling is useful for different purposes. Bringing that all together, again going back to the IPCC reports, and this is now a key finding from the third of the IPCC reports, and it looks at the response that's required to limit future climate change. So back in Paris in 2015, the key conclusion of the Paris Agreement was countries coming together to agree to keep temperatures well below 2 degrees of warming with an ambition to keep them below 1.5 degrees of warming. And this graph here shows, first of all, global emissions of carbon dioxide since 1980, and then superimposed on top of that, the pathway or pathways of emissions that are broadly consistent with a reasonable chance of keeping temperatures below 1.5 degrees of warming. So in a sense, this graph shows the challenge that we need engineers to help the world respond to. And you can see that essentially it's a kind of handbrake turn in terms of global carbon dioxide emissions. And in particular, it means pretty much halving global emissions over the next decade and reaching net zero in terms of carbon dioxide emissions by around about the middle of the century. That's the challenge. As the quote from the IPCC says, all global model pathways that limit warming in line with the Paris Agreement involve rapid and deep, and in most cases, immediate reductions in greenhouse gas emissions across all sectors of the global economy. So I wanted just to, as a last section, to dive into what that means, particularly for the UK. I've mentioned some of the climate impacts that we're already seeing in the UK. Well, what has the UK been doing in terms of responding, in terms of emissions reductions to that challenge? So at the top here, you can see UK emissions since 1990 through to the present day. And I've put up here in blue are territorial emissions, but I've also included the most recent estimates of our consumption-based emissions. So that's taking into account the fact that we effectively offshore some of our emissions by buying goods and services from overseas. And you can see that in both cases, our emissions have fallen. And in fact, since 1990, our territorial emissions have almost halved, whilst at the same time we've seen a growth in the economy. So GDP, we managed to, as a country, effectively decouple our carbon emissions from our GDP, which is something that many people consider to be important. I've also included down here just how those emissions break up down between different types of greenhouse gases. Carbon dioxide is the predominant source of greenhouse gas emissions in the UK, although there are other greenhouse gases, methane and nitrous oxide in particular, that are also important and come from different sectors. The other key thing is what sectors of the economy are contributing to our UK greenhouse gas emissions, because that's then where engineers can start to come in and look to see how we can reduce our emissions across those different sectors. So what's shown here is exactly the same data in terms of our emissions reductions since 1990, but then broken down across these different sectors. The sector that you can see in dark blue is the energy supply sector, and that's the sector where we've seen the greatest drop over the last 30 years. And we've essentially energy supply, the emissions from energy supply are 30% of what they were in 1990. And that's come about predominantly because we no longer, to any significant level, use coal as part of our energy generation. It's been the main reason. All the rest of the sectors, you can see very little change in. If you look at transport, you can see a slight dip down in the most recent year we have official data. The most recent year we have official data, you can see a slight dip down, and that was because it was the pandemic year and transport emissions were just lower during that pandemic year. But across all the rest of the sectors and transport as a whole, you can see very little change. And the challenge is that every single one of these sectors over the next 30 years needs to reach net zero. So we need transformational change across every single one of these different sectors. So that's when the challenge for engineers comes in, and we're actually a story that, from a scientific perspective, is quite a story of doom and gloom, turns into a story that's actually, I think, about quite a lot of exciting opportunities for engineers to come in and think about how we can do these things differently. The Committee on Climate Change, and obviously policy is important underneath all of this as well. the Committee on Climate Change now produces a regular assessment of the UK's net zero plans, and broadly, back in the summer they produced a report that said in terms of energy supply and transport, there were reasonable plans in place for net zero associated with those. But in terms of the other sectors of the UK economy, currently there are either significant risks or insufficient plans associated with net zero. Picking just two examples here, just to dive into a little bit more detail, and then Peter's going to come in and he's going to talk in a lot more detail about where there are opportunities across each of these different sectors. So a sector where the UK, and indeed globally, there are really, I think, quite a clear path in terms of decarbonisation is transport. And this is looking specifically at surface transport. In the UK, most of the emissions from that sector comes from cars, as you can see in the top graph there, although other forms of surface transport are also important. And we know that electric vehicles are taking off at a really extraordinary rate. So some recent months, it's been as much as 25% of all new cars sold in the UK were battery electric vehicles. I looked at the most recent data available, which was August 2022, and in August, 15% of all new cars sold in the UK were battery electric vehicles. But it's really starting to take off. Obviously, there are significant challenges, though, in terms of the infrastructure that's required associated with them. And in terms of the research, there's also still a lot of research being undertaken, including in Cambridge, associated with the batteries themselves. How can we improve the efficiency? How can we improve the environmental impact and indeed social impact of the batteries that are essential to those electric vehicles? There's still a lot of opportunities for progress in terms of the research and development, but there's a clear pathway to a decarbonised future. One of the biggest challenges for the UK, as everyone will be very aware, is in terms of our building stock and our incredibly inefficient and mostly fossil fuel powered heating of our building stock. And there's a much less clear pathway, not in terms of the technology particularly, but in terms of the policy frameworks for how we go about decarbonising our buildings. And actually, perhaps I should just say that on the building side of things, buildings and transport, in both instances, another key role, I think, for engineers, and one that really did start to come through in the government's net zero strategy, was the important role that engineers can play in helping to use engineering expertise to understand these things from a systems perspective. So to understand transport from a systems perspective, and where actually, in terms of that systems thinking, where the key barriers to significant transformation of that sector might be, and similarly actually looking at buildings and the built environment from a systems perspective and understanding where the barriers to change are. So it's not just in terms of the technical expertise, it's often in terms of the broader thinking that engineers can bring to some of these challenges that's really critical. So that's the UK. The last thing that I was going to mention is how does that all sit in terms of the global response, and because we're in the middle of COP27, there have been quite a number of reports that have come out just in the last week or so looking at the global response. Broadly, the challenge is that the world is simply not moving fast enough towards a net zero future. Different reports that have come out in the past few weeks have highlighted areas where there's particular challenges in terms of the response, whether that's in terms of some of the key policies that need to be rolled out to accelerate that change, or where it's in terms of actual technological gaps where research and development is required to produce the solutions and technologies that enable that. Broadly, in terms of the policies that are currently in place, we're closer to being on a pathway to a 3 degrees world than we are to a 2 degrees or even a 1.5 degrees world. That's basically the point, which I'm going to hand over to Peter. These are just 4 areas where we're working significantly in Cambridge in terms of helping to develop further solutions. I've mentioned energy storage, net zero aviation, another area that engineers are significantly involved in, is another area that we're working on. Greenhouse gas removal and how we can actually, through technological or indeed supporting nature, actually remove greenhouse gases is another key area. And then bringing that systems thinking into other areas, such as from a systems perspective, how can we look at alternative land management practices, is a final area where there's a significant role for engineers to get involved. At that point, I'm going to hand over to Peter. Thank you.
Well, thank you very much indeed, Emily. That was very interesting, but also slightly worrying. But good evening, everybody, both in the room and online. So that's definitely improved my understanding of the subject, and it's also, as I say, left me slightly worried. Now, this topic of climate change and how we respond to it came out without fail during the period of my presidency of this institution. And every interaction I had across the globe, which by the way was mainly via Microsoft Teams rather than British Airways, the challenge and the opportunity of net zero always came up. And many members said they would appreciate the institution having a stated position on the subject. So that's what I've been putting together over recent months, and I've done it very much from an engineer's perspective. And in particular, what's needed to get a result. And my thoughts are in this paper here, and this presentation gives you the headlines, and it is only the headlines from that work. Now then, let's see, come on. Yes. So the more I investigate this topic, the more I become aware that fossil fuels permeate our lives. Whether it's the fuel for our cars, or the natural gas that we use for heating, or the fertilizers that we use for food production. And we get through something like 15 gigatons, that's 15 billion tons a year, and we've got less than 30 years to change that. It's a huge undertaking, and even if we were to reduce the task by making big savings in energy consumption, it's still a huge task. And that still leads me to say that this is the biggest engineering challenge ever faced by mankind. And that's not hyperbole, it's not exaggeration, it's the simple truth of the matter. So what I'd like to do in this presentation is first of all say something about climate change and the political response to it, then move on to what the future scenarios for energy production and consumption might look like, which I've examined from 3 perspectives. The perspective of the technologies themselves, then how we stitch things together as complete systems, and finally economic, financial and commercial factors. And that then leads me on to quite a long and in fact somewhat lengthening set of critical issues and challenges. Now, what's meant by this term net zero? Well, I think as you all know, it's our response to climate change, it's our solution to the problem, it's how we will achieve the 2015 Paris COP21 objectives. The rather helpful United Nations definition on the subject is that net zero means cutting greenhouse gas emissions to as close as possible to zero, with any remaining emissions reabsorbed from the atmosphere by oceans and forests, for example. And this fits with my idea of the role of engineering, which is that engineering is all about taking ideas and science and technology and doing something useful and improving people's lives. So making those ideas work in quantity and affordably, and providing economic benefits like employment and investment opportunities. So in summary, it adds up to, according to McKinsey, it's a $275 trillion multinational, 30-year project. So it's quite a big one. It's certainly bigger than anything I've ever been involved in the past. This summary is what we're dealing with. It's an infographic which gives a good picture of current greenhouse gases. So those 15 gigaton of fuels that I mentioned previously equates to about 50 gigatons of greenhouse gases. So that's in the form of carbon dioxide, methane, nitrous oxide, and fluorinating gases, all of which have this unfortunate radiative forcing or greenhouse effect. And you can see that they originate primarily from coal, from oil and gas, and from agriculture and deforestation. And the energy produced is then consumed by transport, by heating, both domestically and commercially, and by industrial processes, particularly steel and cement. And we're relieved that what I've said, I think, is consistent with what you said, Emily. They don't contradict each other, the numbers are more or less the same. There are 27 boxes on this slide, and at least 22 of them have got a strong engineering content. And most of the rest relate to agriculture, which I sort of ruled out, but actually you're quite right, there is quite a lot of engineering actually in agriculture. And the political response to these challenges were first agreed in Paris in 2015, and as we all know, a commitment was made to limit atmospheric or surface temperature rise to 1.5 degrees above pre-industrial level. And pre-industrial level was 1850. We as an institution started life in 1847, so we've been there right from the start. And those agreements were augmented last year in Glasgow when the so-called Paris Agreement rulebook was put in place. And also at COP26 last year, more specific national commitments were made by a number of countries, for example, to phase out internal combustion engines by certain dates, or stopping deforestation and reducing the use of coal and methane. So, I printed this double-sided, which makes things a little bit more tricky. So overall, somewhere between, I think, 90% plus of global emissions are covered by some form of national targets. But these are essentially political targets, which then require practical engineering solutions. And as climate scientists will point out, it's quite late in the day, and very urgent actions are required. In general terms, in terms of the actions we can take and the decarbonisation technologies that we might use, the solutions are actually quite familiar to you. The obvious route to improvement is through energy saving, whether it's done by technical means such as building insulation, or whether it's through behavioural or lifestyle changes. But then beyond that, there's the use of zero or low carbon primary energy sources such as wind, solar and nuclear. It's clear that electrification will play an extremely large role. Beyond that, synthetic fuels or biofuels are possibilities, particularly for more difficult applications such as aviation and shipping. And gaseous fuels such as hydrogen could be used as energy vectors, although I do have some reservations about how widely they might apply, or they could be used as a storage medium. And finally, carbon capture and storage can be applied to fossil-based energy sources where we need to retain them. So in summary, these are the main technologies of the future, and they're all quite familiar to us. Now, various organisations have put together scenarios of how these technologies might be applied collectively. For example, the International Energy Agency works a lot in this field, and in the UK, the Energy Systems Catapult and the National Grid do so. And in terms of the work that I've personally been doing, I've used the National Grid scenarios. There are 4 of them which they update annually in July. The thing that strikes me, though, is that they give quite a wide envelope of possibilities. This slide shows an example of the format they use. These are the actual energy flows for the UK in 2020. On the left-hand side of the slide, you have the inputs in terms of gas, oil, and so on. And on the right-hand side are the uses, and you can see the sort of flow of this. And this, I've learned, is called a Sankey diagram. Everyone know that? Ooh, lots of nodding heads. Does anyone know who it was named after? No. Good. Well, it was named after Captain Matthew Henry Phineas Real Sankey. Okay? You're impressed, I can see. Even more, he was an Irish engineer, and even more surprising to me anyway, he was actually president of this institution in 1920, 1921. I can't see it from here, but I presume his name is up there. So anyway, I hope it is. It is, good. Well, you've learned one thing tonight. So, this is a more conventional way of expressing how our energy is used or where it comes from. Natural gas in gaseous form is used for the majority of it forms about 42% of our energy consumption, and it's used mainly for heating. There's a further 6% that's used for electricity generation. 30% of our energy comes from liquid petroleum products, 9% from bioenergy, and 19%, and only 19% from electricity. That low electricity percentage surprises most people. So that means, for example, that although we derive a lot of our energy today from wind, electrical energy from wind, it only supplies actually about 6% of our total needs. And we are much more dependent on gas than I think most people realise. But as far as the future is concerned, these scenarios, the ones described by National Grid, provide a much wider range of possibilities than I expected. So on this graph, the x-axis is terawatt hours per year. So our total energy consumption in the UK is about 1,500 terawatt hours. The red triangles are where we are today, and the grey blocks are where we could be in 2050. So in the case of hydrogen, it's virtually nil today, but we could produce anything between 100 and 400 terawatt hours through hydrogen. Not surprisingly, we see wind increasing by a factor of 6 or 7, similar to solar, but on a smaller scale, and at least a doubling and possibly a quadrupling of nuclear power. And then we could see natural gas halving or almost completely disappearing. And as I say, we can see electrical demand increasing by a factor of 2 and possibly 2.5. But the key point for me about this picture, if you like, is that there is no single master plan. And I'm worried that we're in a situation where it's sort of survival of the fittest. I've described it as a Darwinian process of selection. I didn't realise there were 2 people from Darwin College here today, but you at least you know what I mean. And even more worryingly, maybe it's a process of survival of the loudest. So moving on to energy technology, generation technologies, I think you're pretty familiar with this. As far as primary energy generation is concerned, we expect wind, solar and nuclear to be the main sources, plus bioenergy, to the extent that feedstocks allow. But I can't help but think that we will continue to need combined cycle gas stations with carbon capture for quite some time to come to counter the variability or intermittency of wind and solar, and thus provide the so-called dispatchable energy that we've all come to expect. You know, when we switch our kettles on, we expect the thing to work. But I think in general terms, the supply side of energy is well defined, but with no clear counter strategy to variability. Then, as I've said, the electricity grid will need to transmit at least double the amount that it does at the moment. So that's a lot of wires and switchgear and transformers. In my view, it's a definable problem at the high voltage 400 kV transmission system level, but there's a lot more uncertainty at the sort of low voltage local level, where, you know, and you'll know this from your neighbours, there could be quite an unpredictable mix of solar panels, electric cars, domestic batteries, and so on and so forth. So I think that's going to be a bit of a messy situation, to be honest. And of course, the other thing about the electricity system is it will have to be able to cope with two-way flow of energy. It'll have to have some intelligence, and somehow it'll have to retain the same resilience as the electricity system does currently. The system will also need some level of storage, and frankly, the only technology that's currently proven at a grid scale is pumped hydro storage schemes. There are possibilities with batteries, but if you do the sums, the mass that you need, the weight that you need is enormous. Hydrogen's another possibility, and there are other developments such as compressed air and liquefied air, but they are at a fairly early stage. I think that liquid hydrocarbon fuels will have some roles to play, produced by either biological or synthetic methods rather than from fossil fuels. They could be used in aviation, and many of you will have heard of sustainable aviation fuels, and they could be used on heavy-duty land transport and shipping. But I think there are limitations, as the costs will be high, given the multiple process steps and the energy required to create them. Hydrogen is attracting a lot of publicity. I think it will definitely be used in hard-to-abate applications such as heavy-duty transport, steel, possibly cement. It can be produced either by chemical means from natural gas, combined with carbon capture, or by electrolysis from renewable electricity. But in my view, this is definitely not a silver bullet, as one minister, or recently departed minister, stated. The efficiency of the process from end to end is low and therefore expensive. And actually one of our fellows, who also actually is a professor at Cambridge, suggested that the minister should swat up on the laws of thermodynamics, which for a classicist might stretch him a bit. And then in terms of energy usage technologies, we've made a huge amount of progress on passenger cars and their electrification. They currently represent about 10% of world car sales, a bit higher in the UK. But at the moment, there's still quite a small portion of the world's fleet, about 1%. For heavier land vehicles, which is now I'm interested in, having worked in that field, batteries seem to be moving up actually into more sort of medium duty, and in fact beyond that point. But beyond that, there's competition with hydrogen fuel cells, or possibly hydrogen internal combustion engines, or other solutions such as electrification of through pantographs, or pickup points, if you like, for electricity, which there are experimental systems for commercial vehicles in operation in Germany, and of course pantograph systems have been used for a century or more in rail applications. We've already mentioned synthetic or bioliquid fuels, which could fill some gaps. And as far as buildings or housing are concerned, electrification of heat pumps is likely to be the most commonly used solution, but where possible, district heating systems, and in some instances, hydrogen. Finally, steel and cement making each produce about 8% of carbon emissions. There are methods for abating this, but frankly, at quite an early stage of development at the moment. And then finally, there's some level of so-called negative emissions, that's the capture of carbon dioxide, may be required to compensate for applications where abatement isn't possible. One route, the logic of which I find slightly tortuous, is power stations that run off biofuels, which in the first instance have captured carbon from the atmosphere by photosynthesis, and then they're burnt, obviously, to produce electricity. And then carbon capture systems are used again after combustion to return it into the ground. There are direct capture systems of carbon dioxide working at the moment. This is a picture of one of them, but they're at an extremely small scale, and I must say they do appear to be quite expensive to run in terms of electricity and water and so on. And then finally, further tree planting or afforestation, or probably more importantly, stopping deforestation. That's another route for natural capture of carbon dioxide. Although, again, if you do the sums, that you find that the area you would have to plant if you wanted to make a real impact on carbon dioxide levels. The area you would have to plant would be enormous. So those are some of the discrete technologies. Let's move on to whole systems. Engineers like to advocate a soup to nuts approach. We like to look at, we don't like to look at complex systems in isolation, and that's very true of energy systems. And I think it's also important to say that we need to consider behavioural factors as well as more technical ones. But first of all, one of the critical whole system issues is variability of energy supplies. So, for example, on the 6th of February this year, wind power output over the day in the UK averaged 13.4 gigawatts. Our average electrical demand is about 35 gigawatts. So on that particular day, just over a third was produced throughout the day by wind. But on April the 20th, the output was 1.42 gigawatts, down by a factor of 10. And that gap was made up by gas turbine power stations, which are varying up and down in opposite synchronization to wind. So there, in a nutshell, is the problem of variability. Then there is the issue of materials. Our world is currently built around coal, iron, oil, for example, but in the future it'll be different. It'll be copper, lithium, nickel, cobalt, and so on, for example. And the output of many of these materials, lithium as an example, will need to increase by, in some instances, factors of 10 or 20. And that then starts to bring in geopolitical factors. So, for example, more than 2/3 of the world's cobalt comes from the Democratic Republic of Congo. To its credit, the UK government has formulated a strategic materials strategy. And the Canadian government, which this diagram is from that, has identified 30 critical materials. So that's a critical area. Then there's methane. It's almost as important as carbon dioxide as a greenhouse gas. It's been suggested that as much as half of the temperature rise since pre-industrial times has come from methane. And at COP26 last year, a global methane pledge was made. And whilst we talk a lot about production of carbon dioxide in an operational context, we mustn't forget the carbon that's embodied when we construct a vehicle. We've got a lot of steel in it, or buildings which have a lot of cement in them. And in the case of buildings, for example, the so-called embodied carbon, the carbon that's produced, or carbon dioxide that's produced when we construct a building, is as much as it's equal to the operational carbon over the life cycle of the building. And then the final point I would make in terms of whole system issues is that I think there's a lot that can be done at the level of a firm. And there's a lot that can be gained that can be working through the carbon footprint of a company in the so-called scope 1, 2 and 3 emissions and developing company by company plans to reduce environmental impact and reduce carbon footprint. And in fact, I've noticed that a number of sort of private capital companies are actually requiring these sort of plans as almost a precondition of funding. And that's the sort of thing which will obviously encourage matters. So let's move on now to economics and affordability. The world operates largely on free market principles. To be successful, new solutions will have to be on a par cost-wise with current levels. People just won't buy green steel or green cement if it costs twice as much. But history has shown that consumers will adopt new technologies and will create new markets when products cross an affordability threshold. Huge investment is required there. There are differences of opinion about the exact amount. To achieve the scale and cost reduction of technologies which are currently, I would say, typically at around technology readiness level 6 or 7. As I say, McKinsey have estimated 275 trillion over 30 years, 9 trillion a year. The International Energy Agency has estimated a 50 trillion increment above our current levels. The exact numbers don't matter that much, it's a huge amount of money. But then there is the issue of matching projects to money. Given that investment criteria, particularly for those looking after our pensions and things like that, their investment criteria tend to be quite conservative. And whilst there may be no shortage of money in principle, matching conservative criteria to risky markets, is a bit of a tricky issue. Again, that was recognised last year in Glasgow, and Mark Carney is leading a thing called the Glasgow Financial Alliance for Net Zero. And finally, of course, there is a strong role for governments providing things like subsidies where that's appropriate, supporting early investments, acting as a guarantor or a guarantor of last resort, underwriting markets, pricing carbon realistically, and funding early stage technology, such as, for example, space-based solar power. I had to get that in. Alice wouldn't speak to me if I didn't mention it. It's simple. And consistency of approach, I think, for governments is vital. So not chopping and changing is as important as the interventions themselves. So where are we in terms of progress? Well, you've heard already that atmospheric concentrations of greenhouse gases are continuing to increase. And we're in a situation really where the introduction of non-carbon sources is being sort of countered, or more than countered possibly, by increased use of fossil fuels. In terms of political progress, we've spoken about the various Paris agreements and what happened last year, and the fact that, in fact, politically, a lot of greenhouse gases are covered by national commitments. In terms of technological progress, there is a lot of activity going on, is my assessment. And actually all the right technologies are there. But a lot of them are sort of queuing up to be taken forward at TRL 6 or 7. As far as the whole system approach is concerned, there are gaps, and I keep mentioning variability or intermittency. And then finally, the estimates are that whilst the flow of investment into appropriate technologies is improving, it's not at the required level. And the International Energy Agency suggests it's about a third of the level where it should be. And that sort of matches my intuitive assessment. So the overall picture is one of substantial activity, but rather limited progress. So on that, coming back to what our institution can do and what we can contribute, I've identified 8 topics where I believe that we should be educating our members and we should be influencing policymakers. And these are the ones that I've touched on already. Variability, the seasonality of renewable energy sources and storage technologies to go with them. The management of the electricity grid and how it's done with multiple sources and so on. The role and the scale of use of hydrogen, the supply and geopolitics of critical materials, how we apply carbon capture and utilisation systems, how we retrofit housing and building to make them more energy efficient. An important one, I think, is how we can replicate the empirical and practical engineering knowledge that we've built up with our current energy systems over the last 150 years. And I think that is underestimated. And finally, the role that financial organisations and governments can play in financing and in market interventions. So within our technical strategy board of the institution, we're in dialogue about how we should take these interdisciplinary topics forward. We're not starting from scratch. So, for example, we had a successful conference on hydrogen in March this year, and there's another one in planning at the moment for March next year. And then we will work out a plan as to how to take these other topics forward. So, to summarise, we've got something less than 30 years in which to switch from fossil fuel to renewable energy sources. And as I've said, this is arguably the largest engineering project ever undertaken by mankind. But being optimistic, the technologies already exist by and large to achieve this transition. There are many challenges in making those technologies robust and cost effective, and we need to accelerate our efforts to release cash and engage in a massive programme of scale-up. But as I say, I'm optimistic we'll succeed. It's a challenge, but it's also an opportunity. And there is plenty of work to keep engineers gainfully occupied. So looking at the two youngest members of the audience, if you were to go into this field, I can assure you, you won't be bored. And you can be assured that this work, in the words of the mission of our institution, you will be improving the world through engineering. Thank you.
Super. Well, thank you so much to our two speakers. It really was quite the dynamic duo, wasn't it? I mean, I have to say, there were certain points of that left me feeling slightly terrified. Other areas where I felt a bit more optimistic. So thank you very much indeed for that. We're going to come to the audience in a moment. I'll go in the room and then I'll go back online and then back to the room. But I'm just going to take that sort of chair's prerogative for a moment here too. Unless you've been hiding under a rock, you will have seen Emily quite frequently on the TV recently, emphasising the need to act with urgency here in many different illustrations. I think the first question must be, if there was one thing that you could do, if there was one thing that you could make happen to help us go faster, what would that be? And I'll go first to Emily, and then I'll come to Peter.
Oh my goodness, that is a good question, isn't it? There isn't one thing, right? That is the basic answer. There isn't, and there can't be across any of it. There can't be on the technology side of things because, as we've seen, it does just involve so many different technologies. Both, within any individual sector, it's yet, as Peter clearly pointed out, there's yet to be an obvious winner, if you like, in a particular sector, and it involves the entirety of our global economy, so there can't be. And it's also, again, I think Peter did a really good job of highlighting how technology is a piece of the answer, but it has to sit in a policy context, it has to be augmented with behavioural lifestyle changes of the sort that Peter also articulated. So I think it's an impossible question to ask for one key solution or outcome because there simply isn't one, either politically or technologically. It's the challenge is how do we bring all of it together? But that's also where there's a huge opportunity, especially for engineers.
As I say, you're in very good company here. That was a systems answer. We do like those. Peter, over to you.
I think I'd say two things. I think the critical thing is to get the money flowing. But then the key question is how do you do that? And the one thing that worries me, which I sort of touched on, is that there isn't a sort of coordinating driving force in this. And I think you said on one of your television appearances that there's a real opportunity for the UK to take up a leadership position in net zero technologies and implementation. The thought that goes through my mind was that Phil mentioned that one of the projects I was involved in 6 or 7 years ago, which was setting up a programme office to run the R&D programme for the UK aerospace industry. And that seems to have done quite well. And I do wonder whether we should have a sort of programme office in government for net zero. I think the government is actually doing quite a lot, and if you look at all the specific issues I've talked about, whether it's carbon capture or other things, there are initiatives. But I'm concerned that it's not pieced together and it's not got a single driving force. That's been sort of left to chance almost.
You're complementing each other very well this evening. So we have systems of systems and then coordination, which makes perfect sense to me. Phil, any perspectives from you?
I think there's not a realisation out there as to the speed that we need to act. That's the difficulty. So I think, and I don't know how we get the message out so that people actually realise that if unless we do something, then we're headed into a really, really difficult situation. So how do we incentivise people to feel that now we need to do something? I mean, it's already too late in some areas, but that would be the biggest task I think we've got. The biggest ask is to what can we put in place to make people realise that we have to act.
That awareness and impulse to action, isn't it? Super. So, do we have any questions in the room? We've got some hands up. We've got a microphone. Fabulous. Thank you.
Thanks so much. Hi, I'm Magdalena Matska. I work in base ordinarily, currently working on the Net Zero Review with Chris Skidmore, analyst, economist. My kind of plea / answer to your initial question in terms of one thing we could do, whole systems modelling, really big, really important. Currently really disjoint. So we use the UK Times model within BASE. It's also used by UCL. There are loads and loads of engineering assumptions in there. Some of them haven't really been checked over in a good 5-8 years. If we could join up as an academic community and engineering, science, etc., try to maybe get out of the silos of who owns the model, who gets commissioned to run it, and really come together, that would be great. So your suggestions for how to achieve that, given also the timescales that we've got. Thank you.
Thank you. Who would like to offer a response?
Well, I'll say a little bit. I have pored over the national grid scenario model. Is it that sort of thing you were thinking of?
Yeah, but there are loads,
Yeah, sure, yeah.
It's almost like everyone's got their own.
Yeah.
And how do we bring together the knowledge?
Yeah. I must admit, when I've sort of got into the detail of those, I sometimes stumble across things which don't quite add up. So I do, I do agree that it could do with a case of looking at from an engineering perspective. So it's a matter of how we organise that.
Yeah, maybe I can add something here as well, because we've been, so the example that I gave right at the end on land management is a project that we've been, hugely interdisciplinary project that we're undertaking in Cambridge at the moment, where we're trying to use full systems thinking and approaches and modelling associated with that. And we brought in people from the engineering department in Cambridge to help shape our thinking on that. And very early on, we discovered that actually the people on the conservation science side of things will say, well, we've been doing systems thinking since the very start of the conservation work because you have to. They think about it with a different language and a different way to engineers. And what we're trying to do now is try to get some. We had a very awkward meeting, the first meeting, with everyone, essentially being territorial about they had the best way of doing systems analysis and thinking and modelling. But now we've got to a stage where we're starting to get dialogue across those different disciplines. Sort of thing that I think you're suggesting, let's try and get communities of people who have different approaches to understanding how to do systems modelling together, because I think it's quite clear that it is essential to trying to accelerate and make rapid progress without having wholesale unintended consequences, understand where the barriers are and understand how to accelerate it. I think there's a real, actually I do think it's also an opportunity for the UK again to take real international leadership on this, because we've got all the expertise and knowledge within the engineering and other communities in the UK, and I think we have potential for really creating a blueprint of how to do this.
I think it's so right, it's back to that. There's a real opportunity, isn't there, for international leadership here, and I can't resist a plug for our new strategy that's just been published, which places that emphasis on the fact that the institution is global, but also we've really rebalanced our activities with a real focus on maximising the positive impact of our membership towards society. So we're always very keen to work in partnership with government as a charity to make sure that we can draw on the skills and the expertise of our members for good. Super, there were a few other hands, so I'll take one more from the room and then I'll go online.
Okay, it's Jeff Baker, past president. Firstly, can I congratulate Emily and Peter on a very thought-provoking presentation there. And it's tremendous to see the institution debating this, leading the way, because at the end of the day, it's going to be engineers that have got to solve this problem. And you could argue that engineers caused the problem in the first place. But my question is, I've really got two questions. In order to achieve net zero, the planet has got to be in balance and in harmony. And there's a lot of information, a lot of it came out tonight, on man-made CO2 emissions and where it comes from, and there's a lot of analysis on that. But there's another side of the equation with regard to net zero, which is with regard to carbon absorption in all forms, both man-made and natural, throughout, over the whole planet. Is there data on how CO2 absorption has changed over periods of time? And so we can see where the two curves are actually going. Is absorption, going in the opposite direction, or can we actually turn that up? And the other question I have with regard to CO2 emissions is, how do man-made CO2 emissions compare to natural CO2 emissions that we really can't do a lot about? And I mean, there's sort of methane, volcanoes, other things that are happening around the world. So it's getting the man-made emissions in proportion to the problem that we've got to solve in order to get the planet in equilibrium again.
Right. Of our carbon dioxide emissions each year, about half of those emissions stay in the atmosphere, and that's the accumulating atmospheric concentration of carbon dioxide, and about half are taken up either by the land or by the oceans, and about an equal measure, so about 25% into the oceans, 25% into the land. So those are broadly termed as ocean sinks and land sinks. There has always been a concern as to whether or not those ocean and land sinks will continue to be as effective in a warming world. So the ways in which, for example, the ocean sink of carbon dioxide could change is either through the warmer ocean waters are less able to absorb the carbon in the first place, but also changes in the ocean, particularly overturning circulation of the slow overturning circulation of the ocean, can change the way in which the deep ocean interacts with the atmosphere and change the flux of carbon dioxide between the atmosphere and ocean. So that's concerns as to how that ocean sink might vary over time. Similarly, the land sink, there are concerns as to how that might change over time. Essentially, it's in terms of the growth of plants and trees and so forth, but also the washing of that material, other ways in which that can switch between being more of a source and a sink. And the example that I gave, which is very significant, is in terms of the Amazon rainforest and whether or not that might switch between being essentially a sink of carbon, or a significant storage of carbon, to being a source of carbon. And we see, that's where there's a real concern around deforestation, for example, and the source of carbon in terms of that deforestation. So that's broadly how those numbers add up.
Super. I'm going to come. There's been a question coming online, so I'm going to go to that, but I will come back to the room again. Super. So, a question's coming from Rupert Blackstone. Thank you, Rupert. He says, and I think this is probably for Peter, possibly for Phil. On the wide range of solutions slide, hydrogen is shown on the same graph as natural gas, nuclear, and wind energy, with the potential for hydrogen apparently being shown on the graph as being greater than any of these. Unlike the others, hydrogen is an energy vector and not a source. So where has this hydrogen been assumed to have come from?
Yes, well, I've actually had this conversation with Rupert before, actually, and he is correct to say that I've actually mixed things up a little bit on that slide. You know, I've got two energy vectors in the form of hydrogen and electricity, and I've got, however many things, is it 3 or 4? 4 energy sources. Yes, those are the facts of the situation, and the electricity is produced from wind or solar or nuclear, whatever it happens to be, and then it goes on to power whatever the around cars or houses or whatever. In terms of hydrogen, yes, it is an energy vector, and you can debate, I think, there are two ways of producing hydrogen. The current way of doing it almost entirely is by taking natural gas and putting it through, and there are several ways of doing it, but putting it through some sort of reforming process to produce hydrogen and other products. And you can produce carbon-free hydrogen, if you like, if you put a carbon capture system on the back of that. The other way of doing it, of course, is to do it from electricity, and that's perfectly feasible technically, but the round-trip efficiency or the end-to-end efficiency, that's quite low. So, you know, for every 100 kilowatts of hydrogen that you want, you could easily have to put in 300 kilowatts of electricity. So from that point of view, I think we've still to work out where hydrogen will work economically and what the balance might be in the future between those two, in principle, those two different ways of producing hydrogen. Does that answer the question?
Yeah, I think it is, but I do think it's probably a debate we're going to continue to have for some time, because that's what we're all about, convening, discussing. I'm going to go for one final question in the room. Sorry, there's a gentleman behind who's hand up before I go to the voting fans.
Hi, yes, Simon Edwards from BP, and I also had a question on the hydrogen vector as well, actually. So I think you covered actually 3 points. The first was around, in the course of your work, how critical or important do you see the integration of CCUS and natural gas as an enabler for hydrogen to accelerate the use of it, so effectively blue hydrogen versus green hydrogen? The second point I had was, how did you, or to what extent did you acknowledge the challenges of hydrogen transportation and storage, recognising the difficulty of both of those with the smallest molecule and the fact that it's very, very different and more difficult than methane? And then the third one I had on the hydrogen vector was, what's the latest thinking on the global warming potential of hydrogen?
Okay. I'll defer the third of your questions to Emily, if I may, because I simply don't know the answer. Yes, one of the reasons I said that the sort of efficiency, if you like, of hydrogen systems is that not just the efficiency or inefficiency of the electrolysis process, but also the process of transmission, storage, and so on. I mean, I've had some experience of road vehicles, powered by hydrogen, and you have to put in, big heavy tanks and quite a lot of them, and so on, which sort of detracts. It'll work. There's no doubt about it. But the figures that I've seen for example, for hydrogen-propelled vehicles suggest that they're probably at least could be double the capital costs and double the operating costs of conventional hydrocarbon fuel vehicles. So that was one of the reasons that I expressed a degree of scepticism, if you like, about how widespread hydrogen is likely to be used. So I'm answering your second question now. What was the first one again?
I think it was just around the extent of integration, the reliance of combining, enabling hydrogen through combination with CCUS, basically blue hydrogen versus green hydrogen.
Yeah. Well, again, I think a lot of it sort of comes down eventually to operating economics, and I don't think either process is going to be cheap. Let's put it that way. And it's really a matter of how cheap you make it. And I do know that, for example, in the States they've set this target of is it $1 a kilogram or something like that for hydrogen versus what's the cost at the moment in the States? $12, I think. $8 to $12, that sort of order. I'm getting signals now from me. Seven. There's a family. This is my son who works in this field. You've got it from the Oracle now. $7 a kilogram. So I think there's a big economic argument when it comes to the use of hydrogen.
Super. And Emily?
Well, maybe I can just add, because I think that hydrogen is a really good example of a topic where learned societies like this can play a really valuable role. Because, there are many aspects, considerations, let's put it that way, in terms of the feasibility of using hydrogen for different potential applications, for which, frankly, the numbers can be crunched. And we can look at in a very objective way whether or not they make sense from an engineering perspective or indeed from an economic perspective, for all the reasons that have been articulated. And the issue of the radiative forcing of hydrogen is also one of those associated with leakage from the system, which is related to your second point of it being difficult to transport. And I think that, in terms of helping to provide a robust evidence base for decision-making in government associated with net zero strategies, it is a very fine example where I think there's a really powerful role for learned societies to come in and help provide that evidence base that's rooted in academic knowledge, but also in industry expertise as well, and bringing together that coalition of expertise so that we make decisions that are going to be robust into the future, and we're not making those decisions based on lobbying and vested interests.
Quite so. And conscious of time, it is our tradition to provide a vote of thanks. It's further our tradition that normally a past president in the room gets to offer the vote of thanks. But I thought for this topic around climate, it's rather more appropriate for one of our younger members to provide that vote of thanks. And very, very ably, Myra Boehner stepped up to the breach as I asked her to do this. Literally, she walked through the door there. So I am thanking you for the thanks. Over to you.
Thank you, Alex. Yes, I get the awesome job of saying a massive thank you to Emily and Peter. I think it's fair to say, for myself and probably for other people today, when we come into this lecture hall, when we dial into the webinars, we usually do so with a very critical engineering eye. We are ready to tear your presentations apart. Emily, you did exactly what you set out to do. You hit the humanity on the head. Because today I sat here and felt like a citizen. I felt scared. And you talked about things that affect all of us directly. This isn't something that is affecting our neighbours on the other side of the world. This is affecting our neighbours next door. These are severe floods. They are heat-related fatalities. It's food shortages. And you also opened our eyes to new things like cascading impacts, which is so interesting. So thank you very much for what you did today. It was worrying, but it was also impactful. And I think that would be shared by most people watching today. And Peter, you put the engineering hats back on everyone in the room. Because we've seen it from the questions that we've had afterwards. And it's not just from that technology perspective. but it's also from the other things that make up any engineering project. It is the influencing of policy, it is the total systems approach, and for that I think you've made everyone here feel quite motivated, because let's face it, what engineer doesn't love a good challenge? And so, needless to say, I will be bulk buying the Ladybird book on climate change and managing technology and product development programs, and that's my Christmas list sorted this year. But until I do that, a massive thank you from everyone at the IMechE, a big thank you to everyone in the room, everyone who dialed in, and of course the IMechE events team that make all of this possible in the first place. So, and we also have a little gift for Emily.